radix sorting, and there is a subtle difference between the radix sort and the bucket sort. I told that both are same, right? But there is a subtle difference, okay, little difference between the radix sort and the bucket sort. So more or less both are same. It or like it follows the same type of method to sort the algorithms. Both are meant for sorting the integers as well as the uh, alphabets, right? I'll show the difference between the radix and the merge sort. Sorry, radix and the bucket sort, where exactly the difference is. Just recollect the how the radix sort works, okay? And like previous class I taken, the radix sorts, right? Radix sorts works based upon the number of buckets, right? Um, it it works depends upon the number of buckets, right? So when you look at its complexity of radix sort, when you look at this complexity of this radix sort, see, it takes this much time to execute, okay? Order of d into n plus b. We'll see what is these variables, where b represents the base for representing numbers, okay? For example, if it is a decimal system, okay, it is a decimal system. B is the decimal system. Since it is a decimal system, it is 10. Okay. And what is the value of D? So what is the value of D? How it is calculated? Okay, you know that the radix sort works based upon the maximum or largest number in the array. Once you find the largest number in the array, you will calculate the number of digits in that particular number, okay, and then you will decide the number of passes. So that is the basic idea behind the radix sort as well as the bucket sort, okay. Initially the radix sort and the bucket sort both are same, but when after the first step, it varies. After the first step, the bucket sort and the radix sort varies. Before that, we'll conclude with the radix sort, right? Just I want to tell about the complexity of the radix sort, and d is nothing but how we are going to calculate the d. Okay, it's nothing but the maximum possible value. That's what the largest value in the array, given input array, right? So that's what d. This is how the d is calculated. Order of log k, right? Order of log k. So log k is nothing but here the k represents the number, okay. Then the overall time complexity, how it's calculated, it is the order of n plus b into log b, where you are assigning. So d is replaced with this value, that's all. D is replaced with this value. Once you are replacing the d with this order of log bk, final value is the this one, okay. So don't much worry about on this, just you know what is the radix sort and just know the complexity of the radix sort. And how about this uh, complexity when compared to the comparison based sorting algorithm? See, you have to note on that this radix sort is not a comparison based sorting. See, comparison means that you will compare one element with the other element. Okay, it is greater than or larger or equal to. It's not like that, right? You are dividing the given number of input element into buckets. Okay, you're not doing like any type of comparison in this radix or bucket sort. Okay, that's what. But when you compare, that's what here is mentioned, comparison based sorting algorithm. When this radix sort is compared to the comparison based sorting algorithm, this radix sort takes little bit overhead time to sort the what? Sort the given input elements. Okay, that's what I want to conclude here, right? So just you can know like what is comparison based sorting, non-comparison based sorting, and comparison based sorting. Yes. Next we'll come to the bucket sort. Okay, since you have syllabus in you have both bucket and the radix sort. Okay. So here in this bucket sort, it separates array into smaller groups or buckets and sorts them individually using sub-sorting algorithm. See, this is what the difference. You can note down here. Once it is divided into bucket, okay, once the given input elements are divided into buckets, thereafter what happens within the bucket, within the each and every bucket, what we will do, we will apply the any other type of algorithm, some sorting algorithm, some algorithm is applied over to the each and every bucket, right, is applied over every bucket. Then we are finalizing the sorting method. Okay, then what you are doing, then you are combining the result. Like you think or like merge sort, like it's not equal to merge sort, but it's like the way how you do the merge sort. You just recollect how the merge sort works. We have taken the first unit, right? Merge sort and quick sort. The same fashion it will work. See, in case of bucket sort, you will divide the given input elements into buckets in some depends upon some some characteristics you are dividing the given input element into buckets. Okay, then for each and every bucket you will apply the some sorting algorithm. Okay, it can be any type of algorithm, right? Whatever you prefer, that's it, depends upon the user. Okay, then whatever you are doing, you are combining the result, right? Example also given. See, sorting players by adding into buckets of their team. Okay, so for example there are multiple players are there. You take the IPL matches. What will I do? First I will divide the players based depends upon the team, CSK, Bangalore, like that. I'll divide the players into buckets. Okay, CSK team, Punjab team, like that I will. Then thereafter what I will do, within the Punjab team I will apply some sort algorithm to what sort within the bucket. Once it is done, in all the buckets, then I will combine the all the buckets. Okay, but that's what he mentioned here. It's not like merge sort. It looks like merger, but it's not equivalent to merge sort. Okay, that you have to note down here. That's what here. Just copy elements of each buckets. That's nothing but how we are combining. So I told that you will combine the buckets, right? Just copy the elements of each bucket back to the original array. Okay, or join the head of each bucket to the tail of the previous bucket. Yes, for example like this. Okay, you having some number of elements, 5 elements here. 3 elements is there. This 5 elements is appended to the tail of the previous bucket. That's all. See guys, at any time if you cannot able to hear my voice properly, please let me know. Okay, at any time you can tell me, ping me here in the chat box so that I can repeat it. Okay, if any like fluctuations in the my voice also, please let me know. Okay, no issues, I will repeat it again because I want make it clear, because like bucket sort and radix sort both are same, there is a subtle difference. Okay, so this is what how the bucket sort works, right? And also you remember the radix sort also, how it works. No, this is the difference between the bucket sort and the radix sort. We'll show the difference. Initial pass of both so initial pass of both the radix sort and the bucket sort is exactly the same. Okay, so in case of bucket sort, what happens? What both the bucket sort and the radix sort, you'll put into buckets. The elements are put into bucket. Okay, some incremental fashion. Here they're using incremental fashion because your zero. When you take the numbers, um, 0 to 10. The numbers within the 0 to 10 is placed in one bucket. Numbers within 11 to 20 is placed in another bucket like that. And from the second pass onwards, and from the second pass onwards, the bucket and the radix sort varies. Here in bucket sort, what happens? You will apply some algorithm within the bucket, okay, and combine the result sorted things from each and every bucket and form single array. Right? But in case of radix sort, okay, without further sorting, what you will do again? You take the what is that number of digits? You'll go to the tens place. Initially, in the first pass, you will what you will do? You will sort based upon the ones place, and the second pass you will rearrange the elements and place it in the bucket. That's what re-bucket. Okay, so like this it goes on. So this is the subtle difference between the bucket and the radix sort. Okay, so where it is used, where it is used, it is used bucket sort. Since bucket sort is very simple, right? It's more efficient for dense array. It's used for dense array. Dense array is nothing but where array consists of you can things like matrix also, dense matrix, sparse matrix. You know, right? You know, you're aware of this dense matrix and sparse matrix. Okay, it means that all the elements will take 3x3 matrix. We'll take a 3x3 matrix example. So all the elements are filled. For example, all the rows and columns are filled. It means that filled in the sense it is enabled. It means that there is some connection that you will study in the tree. Sorry, not tree, in the graph. Okay. So I am taking an example of 3x3 matrix. Right. So here all the elements in this matrix are filled. It means that it is enabled. I can say this is an dense matrix. Why? Because all elements. The same way I will take I'm drawing here for a the same 3x matrix is filled with zeros and ones. It's filled with zeros and ones. You can find here. It is filled with zeros and ones. See, wherever the zeros is filled, it means that it's not enabled, it is disabled. It means that it's a sparse matrix. Okay. So dense means that you have more number of connections or more number of elements, more number of elements. So more, if there is more number of elements, we can opt for bucket sort. If it is less number of elements, we can opt for radix sort. So that's what I want to convey here, right? Guys, is it clear, guys? Can you get the difference between bucket sort and radix sort? Shall we move on to the next type of sorting? Is based on what? Priority queue, heap, priority queue, heap, then sorting algorithms. It is divided into three ways, right? Three parts: priority queue, heap, and sorting algorithms. Fine. So here, coming to the heap sort. Before getting into heap sort, you should be aware of heap, right? What is here heap? Why it is termed as heap? Can anyone tell me what actually heap sort uh, is? What heap sort is a binary tree? Can anyone reply me? Heap sort is a binary tree or not a binary tree? Okay. See, when you take this, um, it can be heap. Can be what? Max heap, or min heap. Okay. See, when you are arranging the what tree, complete binary tree. Okay, in either max heap or min heap. It's nothing but if you are placing the if the largest element is in the root, that I can say it is a max heap. For example, 20, 20, 3, 5. See, you can keep like this also. 3 can come at left side and right side you're having 5. No issues. We have to follow the binary tree. Don't confuse with the binary search tree. Okay. Don't confuse with the binary search tree. It is a binary tree. That's all. Left and right elements can be greater or higher, greater or small. No need to bother anything. Okay. So here, when you look at this heap, I call this as a heap. If I delete an element, okay, always in heap you can, there is a only possible element to delete is the root element, that you have to keep it in mind. You cannot go on somewhere else in the delete an element, right? See, yeah, which when you look at this heap, fruit heap, what you will do, which element you will pluck? I mean, you take only this element, this fruit, only the topmost element you will be picking. You cannot pick like at lowest level. One second. Sorry for this one. Yeah. So see, that's what, when you are picking an element from the heap, so you are selecting the topmost element. The same way is applied. If you are deleting an element from the heap, it is a possible way to delete only the root element. No other element is not accessible to delete from the heap. That you have to keep it in mind, right? And there is also insertion. Also, you know that where it should be inserted. That also you very well. You're inserting an element in the heap, where it should be inserted. Always while inserting, you should preserve the property of complete binary tree. It's not like wherever you wish, you cannot insert the element in the heap. Okay, always you have to preserve the property of complete binary tree. Okay, let me share here one second. To take this, for example, for inserting, and we'll always will take the max heap. Okay, whatever the operation we are performing on max heap, it is applicable to min heap, right? First we will take the max heap. Okay, if you are inserting into, if you are inserting an element into the max heap, the same way you can insert an element into the min heap also. Okay, in case of max heap, always the topmost element will be the root element, is the highest element. Okay, for example, 50. I'm taking an example, right? I'm drawing an example for you. Then see, you can find that all the, you know the difference between complete binary and full binary. Full binary is nothing but all the elements except the leaf node, will have the child elements. Okay, that's what the full binary tree, that you know, except the leaf node, all other elements will have what, the what, child elements. Okay, this is the binary tree. Sorry, this is the heap. This is a heap. Now I want to insert, I'm calling the function insert 60. Okay, I'm calling the function insert 60. Okay, where it should be inserted, always it should be inserted, and always you can represent this what, in terms of what, an array representation. Always can be either an array or linked list, right? So this is 50. Okay, 20. You know that, right? You know the binary tree property, 2i plus 1 for the left child. For the left child it is 2i. Okay, if we want to know the right child for the given element, it is 2i plus 1. Okay, 30 and 15, 10. Okay, like this goes on. Okay, it goes on. For example, and let me complete this one. 16. Okay, 30. I left 30. 20, 30, 15, 10, 8, 16. Okay, it's right. Fine. Now, I want to insert 60. So where should be inserted? It's not like I will compare this 60 here. I will compare the 60 here. It is greater than 50. So I will go here. Then again I will compare 30 with the 60. Okay, it is not also possible. I'll go towards right side. So it's not like that. It has to be inserted at the left child of 15. Why? Because we have to maintain the property of complete binary tree. We have to preserve the property. You cannot insert like here. It's not good. Okay, it's not wrong. It's wrong. So always you have to insert at the left child of 15 only. Fine. Right. Okay. Next it is done. What you have to do now? I have to rearrange the elements because so once I after inserting, what should I do? I have to compare with the parent element. Once I done, guys, shall I continue this? Because if you are aware means if you are aware with this means then I don't want to proceed. Shall I continue this, guys? Anyone can give a reply? Okay, I'll continue. I'll continue. Some students are replying. I'll repeat. Nothing is there. Nothing is there. I'll repeat. Nothing is there. See, initially I've taken the uh, heap. The heap consists of three levels. First level is 50. Second level is having 20 and 30. Third level 15, 10, 8, 16. Okay, 8, 16. Now I want to insert 60. Now I want to insert 60 into the max heap. Always you should keep in mind either max heap or min heap. Now I am inserting. Why I am inserting here? Why I am inserting here in the left child of 15? Why? Because I have to retain the property of complete binary tree. Okay, you know that complete in case of complete binary tree, except the what last level, except the last level, all other nodes will be having the child elements. And in addition to that, the elements will be filled from the far left. See, it has to be filled from left to right. You know that. That is what binary complete binary tree property. So uh, if I want to insert 70, it has to be inserted here only. Here only it has to be inserted. I should come from far left only. If I am inserting 80, I should be insert here only. Okay. So I have to fill from left to only, from left to right. That is what the property of complete binary tree. That's what I am drawing here. Okay. I'll erase it. Our goal is to insert 60. Okay. Now it's done. Now I am inserting 60. See, I should retain the property. Always, once I insert the 60, I should check whether the inserted element is in the appropriate place. But now, how will I check it is in the appropriate place? I'll check with my parent. I'll check with my parent. 60 is compared with 15. See, 60 is compared with, I'll erase this also. 60 is compared, where is 60? Now it will take another element. Let me write here 60. Because consider that you're having some number of size array is having some number 1, 2, 3, 4, 5, 6, 7, 8. Okay, the size of the array is 8. Beyond that you cannot insert, but now 60 is possible. Now 60 is possible. Why? Because it is having some free space. That then I inserted. It's coming into the position of the last index. Okay, done. Now I have to compare with my 15. How will I compare? I will compare with the parent. Okay, right. So I like this is compared with the parent. So 60 is compared with the 15. So the same way you have to use the formula to compare with the parent. Okay, divide by 2. Okay, 60 divided by 2, it directly comes here. Okay, so you know that 15 child elements will come here. I mean, the child. I'm drawing the child element. The other one will be here. When you are inserting, it will come over here. Okay, it will come over when you are inserting. It will be come over here, right? So I'm not inserting because the size of this array is 8 only. That's why I'm stopping here. But I can able to find the 60th parent element by the formula divided by 2. Okay, I can find okay 15. Then I will compare 60 is compared with the 15. No, so it is what greater. Okay, I should swap the values. I should swap the values. Swapping here. Okay, I'm swapping here. Now it becomes what 15 comes here and 60 comes over here. Okay, the same way I have to replace here. Just I'm diagrammatically I'm telling. The same way in the array representation, I have to replace here also, right? 60, 50. Okay. Then what I should do? Again, I will compare the 60 with the my its own parent. Okay. Again, what happens? It is what? It is greater. It is greater. So then 60 is compared with how it is comparing. It is divided by 2. It will just apply the same formula divided by 2. Divided by 2. You can use normally you should not use like a floor or ceil operator here to find the parent value, just integer. Okay, just integer is enough. Don't apply any floor value, floor function or ceil function over here. Fine, that you know. So it's again it's compared. Then what happens? 60 is replaced here the same way. Same way what happens? 20 comes over here and 60 comes here. Okay, then similarly it will happen like this also here, right? Similarly it will happen like this also for what happens 60 comes over here and 20 comes. This is array representation. You similarly can do it for linked list also, no issues. Just will be clear with this array representation. Okay, then again what will I do? I'll compare with the root element because its parent 60, the parent is what 50. Again I'll compare. This is compared. What happens? It is again false. I will erase. I'll erase here. Okay, so this is become 50. This is 60. The same way I am doing in the array also 60. So this is the way where the elements which you are inserting is put it in the appropriate position, appropriate index of the array. Okay, now it looks like a max heap. The element which is bigger in the heap is what placed in the right position. Okay, here if you can note down here, always while inserting, you are doing the what is that? The swapping in the upward direction. See, while inserting, always you will swap in the upward, or the adjustment is towards the upward direction. Vice versa. Vice versa for delete. Vice versa for delete. What happens? It is in the downward direction. That we will see. That will see. It is in the downward direction because if you are deleting an element, what happens? 60 will be automatically deleted. 60 automatically deleted, right? Then I should what replace some elements over here, and all the element 60 will be coming over here. That we'll see later. Okay, don't confuse. This is what insertion of the max key. Fine. So what is the time it takes now? What is the time it is taking? Because since it's the binary tree, it depends upon the number of swappings. Number of swappings. It is order of log n. It is order of log n. The time taken to insert an element in the max heap is what? order of log n. Okay, and can you tell when it will when it will be order of 1? Can anyone tell? Can see, for inserting 60, it is taking order of log n time. Depends upon the number of swapping or a number of height. See, this is what n is nothing but the height. Okay, n is nothing but height of the tree, because it depends on the height only you're swapping. No, level by level you're moving upwards. You're moving upwards by level. So okay, anyone tell when it will become order of 1? When it will become it is minimum? Can anyone tell? So till then I'm inserting 8. Okay, where will I insert? Sorry, before that I will have to. I can insert. Let it be here. Let it be here. I'm inserting 8. Let it be the maximum. I'm inserting 8 over here. I'm inserting here 8. Once I insert 8, what will I do? I check for the pattern element, whether it is greater or not. When I'm checking, no swapping required. So that is what. So therefore, if you're inserting an element in the max heap, which is the parent element, there is then only the minimum time is required to minimum time required for inserting. Guys, can you understand now? Can you understand now? Can you understand now? Why when okay? For example, I'm inserting now 9. Where will I insert? Here only I insert. I insert here only, right? I'll insert 9. What happens? After inserting, I I'll check with the parent element. No swapping required. So it takes only order of 1. Okay. See, this is the case of max heap. The same way you do it for min heap also. Min heap here what happens? It will keep only the minimum element. See, which is the minimum element in this heap? Here also duplicate elements are there. Okay, just try to avoid the duplicate elements. Okay, try to avoid duplicate elements. Let it be what 21. Okay, so the minimum element in this heap is 8, right? The minimum element is 8. So 8 will be placed in the root element. In case of min heap, I'm telling about the min heap, right? And okay, now others, can you hear me, guys? Others, can you hear me? Whatever I said now, it is clear, no? Whatever I said is clear, no? So I'm going to do the delete operation. Okay, it's 20. I'm just drawing the heap now. I have to follow the complete binary tree property also. Okay, I have done. Okay, I'm done. Now I'm going to delete an element from the max heap. So I know that it's a, from by observing this, I can come to know that it's a max heap. Okay, okay. Now I want to delete. Where will I delete? It is always, that it is possible to delete only the root element. There is no other option. There is no other option. Okay, the same way this heap can be represented in array also. You can represent array also. Just assume that it is placed in the array representation. Okay, now 50 is deleted. Okay, done. It's deleted. Now who has to come to this position? Okay, that is a question now. Who has to come to this position? Can anyone tell what you will do? Either 30 should be placed or 20 should be placed. Can anyone give a reply? And why? What is the reason? 30. Why? what will I do? I will compare the elements in the second level which should be placed. Okay, it's not like, because it's not like max heap. It's not like because of max heap I cannot like place the 30. Okay, okay, I have to compare. Yes, whatever say is max heap, but before that I have to compare the level. I have to compare the level, right? 30 and 20. Okay, right. I am telling that. Okay, this is what 30. 30 is greater, right? 30 is greater. Okay. So which element you will be removing now? Which element will be removed now? Can anyone tell? So now that 30 is placed over here. 30 is placed over here. Okay. Okay. Which element should be come here? Can anyone give a reply? Which element should come over here? Which element, which numbers will occupy the place? Occupy the left child of root element 30. 16, yes. Because what? I have to remove the only the last element. I cannot simply like remove this 50. I cannot place this 15 over here. Okay, I cannot place this 15. Why? Because if I remove this 15, what happens? I'm violating the rule of complete binary tree. So always I will choose only the last element from the binary heap. Okay, this 16 will be placed over here. Okay, 16 will be placed over here. I'll erase this. Can you understand, guys? Okay. So what the other way you can do one thing that I will tell later in the next class. There is some differences there. Okay. So this 16 is placed over here. Again, next question. What is the analysis? The time taken. Again, it depends upon the number of what is the height of the tree. Height of the tree, right? Height of the tree again nothing but what? Order of log n. It takes log n. Or log n time to delete an element from the heap. It depends upon the time. Is it clear, guys? Okay. Now, if you do this, how you are adjusting? If you look at this, if you observe this, what happens? You are moving downwards, right? You are adjusting the elements towards downwards. Okay. So that's why there's a difference between inserting and deleting. Okay. In case of inserting, you will be adjusting from leaf node to the root node. In case of what is that? Deleting, you do the adjustment from the root node to the leaf node. Root node to the leaf node. Okay. And then one more thing you can note down here. What you can do, it is considered that how many elements are there? 1, 2. Previously there are 7 elements. Okay. Before it was what is that? Now it is 30, right? 30. After a day, after deleting 16, 20, 15, 10. Oh, no, yes, 15, 28 is right. 8. Okay. So what is this space? It's nothing but we have deleted an element called what is that? 50. We deleted an element called 50. What we can do, instead of throwing it away, like instead of throwing it away or deleting or just ignoring that value, we can place that 50 in the empty position or the vacant position, because a vacant is created, right? The size of the heap is this only. The size of the heap is this one, but there is a vacant space. There is a vacant here. There is a vacant here. Instead of ignoring that deleted value, we can place the 50 over here. Okay, you can place that 50 over here. Why I will tell? Why? Because if you try to delete another element, you try to delete another element from the max heap, what happens? What happens? 30 will be deleted, right? Guys, are you following? I hope you are following. 30 will be deleted. Okay, 30 will be deleted. And what you do, you need to remove this 8 also. Why? Because this 8 has to be and should be placed in the appropriate position. Where you will put now 8 here. What you will do, you will put 8 here, right? Now 8. Then you start comparing. Then you will start comparing whichever is greater. You will place appropriate. You will place in the appropriate position. That is okay. That we will see later. Okay, but after deleting deleting this 30, what can, instead of ignoring that, what you can do, you can place that 30 in the vacant position, because one vacant is created, right? Because one vacant is created. Now the size of the now the size of the heap is what? 1 2 3 4 5 elements. Vacant is 2. Vacant created is 2 space. But in that vacant, I don't want to leave it simply just placing the deleted element in the appropriate position. It's not in the appropriate, just placing the deleted element. If I keep on do this, if I keep on deleting the elements, what can I do? I can place the deleted element into the vacant position. See what happened. The next largest element will come over here. What happens? What is the next largest element? Element 20. Yeah, yes, 20 will be coming over here. Okay, so like that it goes on. Next largest element, like that it goes on. You are moving. Just look at the towards backwards. When you go backwards, what happens? You are placing the highest element will be in the last position. Next largest will be in the last push. Last before. Okay, next largest element will be the before 30. Okay, now it gives the ways for sorting. It gives way of, like, you to sort the elements. Instead of ignoring that element, just I am keeping the deleted element in the vacant position. Okay, so this gives the way of heap sort. So for detailing, we can see tomorrow also in another session. So here I conclude that instead of ignoring the value, I will placing the deleted element in the vacant position created in the size of the array.